Hi, this is Warren Powell. This is part one of a talk that's based on a talk I gave to Gurobi optimization. It's on a universal modeling framework for sequential decisions, bridging machine learning and stochastic optimization. So this is the wallpaper that I use to describe all the projects I've worked on. I've done a lot of work in trucking, worked for a number of years with Norfolk Southern, optimizing locomotives, air cargo, mainly with the military. I ran an energy lab for 10 years, did a lot of work in health. Lower left-hand corner is a robotics scientist. I worked with material science for about 5 years. I listed all the general areas I've worked on, and I feel like I've sort of covered all of humanity. Everywhere we have an activity that involves people, they're all making decisions under uncertainty. Now, what they're trying to do is to improve something, maybe increase profits or reduce costs, but maybe they want to increase the strength of material or cure disease or increase the yield of a manufacturing process. Now, we start with a step that's I refer to as framing the problem. If you want to run a better supply chain, energy system, health system, anything, you have to make better decisions. So I start with three questions. What are your performance metrics? What decisions do you have to make and who makes them? And what are the sources of uncertainty? So these three questions kick off our start in how to approve it. This is the step of framing the problem. Now, what do we mean by a problem? I have found that problems tend to come in two categories. One is decision-focused problems, where I know the decision. I want to locate a warehouse, order inventory, or route trucks. And then there's metric-focused problems where I have a metric. I need to reduce the cost of this cement factory. I need to increase the sales for my startup. I want to maximize the strength of the material that I'm trying to produce in the lab or reduce defects in the manufacturing process. And then it's up to me to start figuring out what are the decisions that I can use to achieve this performance. Now, through this talk, I'm going to highlight the achievements of two, what I call titans of optimization, George Danzig and Richard Bellman. And conventional thinking is that linear programming, popularized by Danzig, is a powerful tool widely used for many applications. Dynamic programming, on the other hand, pioneered by Bellman, is elegant theory, primarily for PhD students and with limited applicability. Over the five parts of this talk, I'm going to reverse this way of thinking. And in part four, I believe it is, I'm going to present this slide again, but I'm going to come up with different conclusions and hopefully change your mind about this. Now, the talk is divided into five parts. This is part one. I'm going to start with the step of optimizing decisions. So if we take a look at my wallpaper, behind this is a number of questions. And if you look at any one of these boxes, there's a question where I have to make a choice. So because I have to make a choice, that's a decision. I want to make the best decision. Now, decisions can come in three flavors. One is physical decisions that manage inventories or schedule nurses, locating facilities. There's financial decisions, where I'm managing cash flows, pricing, arranging loans. And then there's decisions to move information. I can be sending or receiving information, running experiments to see how it works, testing drugs and marketing. Now, let's take a classic optimization problem, airline scheduling. So this was a really major breakthrough in the OR community in the 1990s. We can take this language of math programming, so I'm showing a linear program here, but it could be an integer or a nonlinear program. And I can go out to a complicated real-world problem like an airline, collect data, and output an airline schedule. And this was a major breakthrough in the 1990s. So the language of math programming, it's very powerful. It's spoken around the world. Many books roughly approaching the problem the same way with the same notation, the same modeling framework. There's computer packages that are available to solve realistic problems, and thousands of graduate students coming out learning how to speak this and operate these tools. All of this is due to this book by George Danzig and the work of George Danzig in the 1950s, where he developed a simplex algorithm where we made this linear program useful. It went from being sort of an elegant little bit of mathematics to something that can actually solve real-world problems. Now, I like to use this crowded urban street. Now, well, let's just imagine that these are all young urban professionals, pretty much all college educated. And I like to ask the question, how many of these people do you think have even heard of the term linear program? I think very few. Now, how many of these people make decisions? Well, the answer is all of them. Making decisions is a fundamentally human process. Now, I like to think of decisions as being sort of the small fish in the sea. There's many of them, and they come in various shapes and sizes, but they're all fairly small. Uh, and then there's math programs, linear and integer and nonlinear programs. These are like the whales, and the whales are very important and they're big and high impact. But a fisherman can spend his entire career in the sea and never see a whale. Now, the problem that everybody is solving, that problem, the little fish that everybody sees, is taking a set of discrete choices. There could be two, there could be 10, there could be hundreds. Um, and the thing is, I need to find the best one. The challenge is I don't know which one is best. I don't really know how each one performs. So I had this uncertainty, and this is a problem class that has been debated for 2,000 years. There's countless versions of these things. This is a sequential decision problem that we'll talk about later. But this is the universal problem that arises everywhere. Now, when you try these problems, I may try a particular choice and I learn from it. Learning problems can be very inexpensive. They take microseconds to seconds, maybe minutes. This often happens on the computer. And then there's expensive experiments that take an hour to a day, up to a month, maybe even a year. And these are expensive experiments. I can do offline learning, which is where I'm learning in the lab or in a simulator, where I can do experiments where I don't care if I do badly, I just want to have a final design. And then online learning, where I have to learn while doing, and I have to learn as I go in the field, and if I try something that doesn't work, I have to suffer that mistake. Now, these learning problems, there's an entire spectrum from physical resource allocation with no learning to pure learning problems without anything physical moving around to the mixed problems. Now, those mixed problems actually occur quite a bit, haven't received much attention. So now let me go from static to sequential optimization. Here's a basic static optimization problem, a linear program, or any math program. Now, when we solve this problem, we're solving it at a point in time. We have data, the matrix A, B, and vectors B and C, and I know them at this point in time, so I'm going to go ahead and put a time index on them just to indicate I'm solving this problem at time t. Now, the solution to this, argmin means let's take the x that optimizes this. This is now a function, and it depends on the data. I'm going to call the data st. S stands for state, but here the state is the matrix A and the vectors B and C. So A, B, and C is the data for the problem. That's our state variable. This is what we know at time t. And my function here is to solve this linear program. Now, often when I'm solving these linear programs, I know that I'm not just solving them once. I'm going to solve them repeatedly. And I know that my solution might impact the future. So often what I'm going to do is I'm going to put bonuses and penalties, and I'm going to tweak it in a way because I understand that when I solve it at time t, I have to think about the impact of my decision on the future. So now I have a parameterized linear program or deterministic optimization. So I'm going to express my policy x pi as dependent on the state st, that's my data, and some set of tunable parameters theta. So let's say I start at time 0, I have my data. I call my policy and it gives me the decision. Now, new information arises from outside the system that I didn't know what this was when I started. And I step forward to time t and I do it all over again. I have an updated state, make an updated decision. Now I get new information, and this proceeds over time. I can, at every point in time, I can add up some sort of performance metric at how well I do. The sum of these performance metrics is the performance of my policy over time. So now what I've seen is two optimization models. We have the surrogate optimization model used for making decisions at a point in time, and the actual objective function is how well did my policy work over time. So that's the actual objective that anybody would really care about. Now, here my policy is a deterministic optimization problem. Little f is the structure of the linear program and how I've parameterized it to make it work well. And then theta is any tunable parameters for that parameterization f. Now, I evaluate my policy by simulating it over time. And finally, I'd like to find the best parameterization f. And of course, for every f, I need to have the best set of tunable parameters. So even though I'm using deterministic optimization to solve it at a point in time, this actually is a stochastic optimization. I actually think most so-called deterministic optimization problems are policies for fully sequential problems. Okay, so I'm going to pause here. This is the end of part one, and I hope you continue with part two.